Let's talk about becoming a game developer. Making your own video games is an amazing experience. Bringing all of your ideas to life and giving others the chance to experience your hard work is incredibly fulfilling. You will probably ask yourself, how do I get started? How do I do anything in this crazy program? How do I even install the software? Everybody had to start completely new at some point. My goal is to help you get rolling as quickly as I can while still teaching why things are the way they are. This video is targeted at somebody that is brand new to Unreal Engine and game development. In this video, I will walk you through installing Unreal Engine and how to move around in the editor and what some of the important buttons do. I will also start with some basic coding to get you comfortable working in Unreal Engine 5. Welcome to your journey in making video games. Let's begin. First, we need to install a version of Unreal Engine. We can do this through the Epic Game Launcher. Using your favorite search engine, find and download the launcher. Open the downloaded file to install. I've already installed it, so mine looks different. If you are installing for the first time, just keep clicking Next until the installation is complete. Now that the launcher is ready, you can open it and log in. On the left, click the Unreal Engine tab, and then at the top, click the Library tab. Here we'll show the installed engines, recent projects, and add-ons that you have available. To install an engine version, click the plus marker next to the engine version, and in the drop-down, you can choose any of the available versions. For this video, I'll be using version 5.4.1. After selecting your version, press Install and follow the prompts. After a while, you can press Launch to start Unreal Engine. This will take you to a project setup screen. In Unreal Engine, projects are what we call your game. This screen has a variety of templates to start your project with. Each has relevant and common assets used in that project type. Assets are the files used in your project. For example, the first-person template has a default character that only has arms, while the third-person template character has a full body. Neither import the car model from the vehicle template. You can always import assets from other templates later if you need them. Take your time and find the closest template for your project idea. For this example, I will be creating a third-person style project, so I will use the third-person template. Make sure Blueprint is selected under the project defaults, select Starter Content, and name the project to whatever you desire. These can always be changed or added later. If you have a high-performance computer, you can leave the quality preset to maximum. Elsewise, you will want to change this to scalable. Once the details are configured, press Create to start your project. After a few, the editor will open. I will reset my layout to default to make things match yours. If you accidentally change or move a panel, you can reset your layout to default the same way. We are now looking at the level editor screen. The level is the portion of the world the user interacts with. Your project can have one level or as many levels as you want. On the screen, there are several panels to use. The toolbar is the shortcut area of the screen. The most used functions are used here. You can save or open a level here, change the work style quickly, place objects in the level, change the level properties, and add sequences. There are also controls to run the project and control what systems the project will run on. I will cover the uses of these throughout the video. The Place Actor shortcut is important enough to me that I prefer to have the panel docked for even easier use. Find this in the window portion of the menu bar. Actors are the things that you put in your level. This includes things that you can see, as well as invisible things like sounds, trigger areas, cameras, player start points, etc. The level properties and world blueprints control how the level acts. We will jump into that shortly. Sequences are typically used to create cutscenes. This might be beyond the scope of the beginner video, and will most likely be in a later video. The player controls allow you to test the level. Press the green play button to start testing your level. In the third-person template, the default player controls are common WASD controls. We will cover how to change these settings in this video. While working in the editor, the navigation controls are a bit different. Still, the easiest way to move around is to hold the right mouse button and use WASD to fly around the level. We'll cover the platform settings in another video. On the right side is the World Outliner and the Actor Details panel. The World Outliner lists everything that is placed in the currently opened world. I will select a mesh and press F to zoom into that actor. Meshes are the things that you see and have a shape. Unreal Engine is very limited in creating meshes. Typically, meshes are created in other software like ZBrush, Maya, or my favorite, Blender. Once you select an actor, the details about that actor are available in the Details panel. There are many details, so I will pull the panel up and dock it with the World Outliner so I can see things better. Here, you can see and change various details about the actor. The Details panel is split up under multiple headings to keep things organized. For example, in the Transform heading, you can control the location, rotation, and scale of that actor. There are many details to view or adjust, and we will cover them as needed. The menu bar contains the bulk of the settings and functions that you will need while using Unreal Engine. In the File section, you will find all of your saving, opening, and exporting for the project. The Edit heading has your copy, paste, undo, redo, along with access to settings, preferences, and plugins. The Windows heading gives access to adding panels and changing layouts. We won't be using the Tools heading in this tutorial. The Build heading gives you all the controls for preparing your game to be packaged. We will discuss this more near the end of the video or another video. The Actor heading gives a lot of control over the selected actor and functions when multiple actors are selected. We will cover these as needed for this tutorial. Finally, there is a Help tab for viewing various documents and if you're searching for answers on your own. I recommend reading through each of these on your own to get a better understanding of Unreal Engine. In the top right, there is a quick access to the settings. These options will either open a panel to adjust the settings or a whole other window that can be docked into your tab bar. The plugin settings allow you to add or remove plugins that control how the editor behaves. Typically, plugins add functionality to the editor that is not always used. These are not turned on by default to keep performance at a maximum. As you progress using the editor, you will find plugins that are worth turning on, but for now, we will not enable any for this video. The project settings will most likely be the most used settings while using Unreal Engine. In this settings tab, you can change many things about how your project behaves and launches. You can change the project thumbnail, add copyright and developer information, if it starts in virtual reality, or thousands of other things. We will cover portions of this as needed in this video. The content drawer or asset browser is where you keep all of your assets or files and gives you the ability to keep them organized. There are many different types of assets. Let's start with opening a new level that is provided in the starter content. Level asset files are commonly known as map files. To open a saved map, you just double-click on it in the content browser. When opening a level for the first time, there will typically be a delay as shaders need to load in. Don't panic if things don't look as expected. Sometimes you just need to wait a little bit. Shaders can sometimes take a very long time to fully load. Open the starter map provided in the starter content, found in the starter content and maps folder. This level is provided to show examples of how different actors are used in the level. Once all the shaders have loaded, you will see that there are examples of different materials and how they look. There is also an example of a physics simulation. If you click on the three dots next to the play button, you can choose Simulate to start the physics engine and see how these shapes fall within the level. You can do the same process to then select Play in Viewport and be able to walk around this level with your third-person character. This will also run any physics simulations. In this example, you can also see effect and particle examples, as well as various lighting examples. Use this area to get comfortable moving around the level editor and using the various controls. If something gets broken or goes wrong within this level, it's not much of a big deal to reload it exactly as it was. Covering the last couple of things in the level editor, There's an output log. This is a text representation of every single thing that happens within the Unreal editor. As you can see, this gets flooded with information very quickly. We will discuss filtering this down to be more useful in this video. Finally, there is a command prompt. This allows you to alter editor and project settings quickly without having to navigate the menu. Personally, I don't use the command prompt very often, but it is nice to have to do something quickly. Let's create our own level. There are a few ways to create a new level, but going to File and then New Level and selecting Basic is a great way to create a level that has all the basic lights, skies, and clouds already there and ready to go. Once your level is created, name it and save it. When creating asset names, it's always a good idea to put what type of file it is at the beginning. Also, when naming a level, you cannot use spaces. So for this level, I will add map underscore to the beginning of my name. This is a good habit to get into early to keep your files organized. You can see that it created a file in the content level of my content browser. To keep things organized, I will create a folder named Levels and move this level into that. Sometimes when moving files around or renaming them, you will get a pop-up message warning you about an error. Unreal Engine keeps track of where files are located and directions how to use them. Renaming or moving some files can break those directions. If you get one of these errors, it's usually a good idea to right-click on the content folder and validate the assets in the folder. This makes sure all of the assets will work properly, and then update all the redirector references. It is usually safe to delete all the unused redirectors. This process updates the directions and location of all of your asset files within Unreal Engine so it knows how to use them. We now need to tell the Unreal Engine to use our new level as the startup level when we open the project. Go into the project settings and click on Maps and Modes or search for Map. Here you will want to change the editor startup map and the game default map to our new level. If you ever go to open your project and the editor goes to the initial template level, don't panic. Your level should still be saved and can open it from the content browser. This just saves a step. Let's cover the actors that are set up in the basic new level. When you select an actor, you can use W, E, and R to change how you interact with that actor. The directional light acts like the sun. This creates an infinite plane of light and shines in one direction. Press E with the directional light selected and change the rotation. You can see the light change. You can set the look of a particular time of day like this. You can also change the settings in the detail panel to change the color and brightness of this light. The exponential height fog obscures the distant horizon and makes the sky transition less jarring. Change these settings to change the color intensity of the fog until you get the feel you are after. After you change a setting, an undo arrow will appear next to the setting. Click this to return the value to its default setting. The sky atmosphere is what affects the directional light to create the time of day. Changing these settings is really only useful if creating a project on an alien planet. Typically, I leave the sky atmosphere, sky sphere, and sky light alone. Again, just playing with the settings in the detail panel will change the appearance of the clouds. Play around with it until you get the look you are after. In the level, the floor mesh is the ground. You can change the material of the ground or the size of the floor. Let's look deeper into putting actors in the level. We will use some basic shapes to start with. Select Shapes in the Place Actors panel and drag a cube into the level. Use W, E, and R to change how you position the cube. Press Q to only select and not move anything. You can use the tips of the widget to only move along that axis, the diagonals to move along that plane, or the root to move in all directions. The widget is good for rough positioning, but the Details panel will let you be more precise. Something you will do a lot is place objects on the floor or on top of other objects. This can get tricky from time to time. The fastest and easiest way is to select an object you want to move and press the End key. This will snap the object to the surface below it. While I'm talking about making things easier, let's say you need to move something past the edge of the screen. You can either zoom out and lose precision, or you can hold Shift and drag a direction. This will keep the actor centered and move the world around you. Hold Alt and drag a transition direction, to quickly make a copy or duplicate. I'm going to move these cubes in front of where the player's spawn area is, so we can see them when I play the level. You can see when I press play, the cubes remain where I put them. I can jump on them and climb them like stairs. Something I forgot to mention while I was originally recording: the mobility settings. Setting an actor to static tells the engine, you don't need to watch this closely because it will never change or move, and it will not hinder performance very much at all. Stationary tells the engine that this actor can change but not move. It really just needs to watch the shadows and reflections. Other than that, you can ignore this. This is a medium performance setting per actor. Movable will constantly monitor this actor. Because of this, the engine will dedicate the most resources to watching this actor and recalculate the required data often. Each setting is sometimes needed, and you should make sure that each actor is set to the best mobility that meets its needs. You can change the mesh and material from the details panel. We can make it blue. Let's make it wood-colored. Simulating physics is a jewel on Unreal Engine's crown. Setting Simulate Physics to True will tell the engine to change its transform and rotation each cycle based on what the physics system calculates for the next cycle tick. You can see that the block falls in a realistic way. Changing to Simulate will show it falling without spawning the playable character. While simulating, even if you move the actor, physics are still being applied to the mesh and will fall when released. Stopping the simulation will return everything to the starting places. The simulated weight of the actor controls the calculated mass of the actor object. Obviously, the heavier it is, the harder it is to move. You can change the mass of the actor or allow the engine to calculate the mass by its size. You can see that when I change the scale, the mass changes unless I override the calculated mass. Let's add a ball that will simulate physics also. When we run the program, you can see that the ball rolls along the ground. Currently, both the ball and the floor are perfectly smooth and flat, and the ball will never stop. You can change this by adjusting the linear and angular dampening. A high linear dampening value slows the movement in a line. Typically, this is any sliding that is happening. The ball is rolling, not sliding, so this would have little effect on the ball. A higher angular dampening value slows the object's rotation. When I raise this, the ball doesn't roll as far. I'll turn off gravity for the box. Since the linear dampening is very low, the box will float away forever like it's in space. If I raise only the angular dampening value, you will see that the box still floats away but isn't spinning anymore. Adjusting the linear dampening value now causes the box to float away a little, but stops after a short distance. Constraints prevent the actor from being moved along a particular axis. In Unreal Engine, each axis is color-coded. X is red, Y is green, and Z is blue. You can see that I can prevent the actor from moving along different axes or rotate on that axis. The rest of the settings are beyond the scope of this video, or will be covered later. Let's take a second to look at world space and local space. I placed a cone into the level and moved it to world space 000. And then up 50 units to set it on the floor. As you can see, the green Y-axis points to the right, the blue Z-axis points up, and the red X-axis points away from the screen. These are the positive directions. If I drag the cone to the right, the Y-axis value increases. Same if I lift it upwards, the Z-axis value increases. The X-axis value increases when I move the cone away from the screen when looking at it from the front. This icon switches controls between world and local space. World space is where the object is positioned and rotated in the world. Local space is how it's positioned and rotated compared to itself. Imagine that the cone point is up, like your head when you are standing. While standing, your head is up in both world and local space. But what if you laid down? Which way is up? Is it towards the sky or towards the top of your head? In world space, up is always positive Z, no matter how the actor is oriented. In local space, up is towards the top of your head or the cone point, no matter how the object is oriented in world space. You will see that local Z always points to the cone point. It is important to understand and remember this difference. Before we move on, let's explore the last few buttons in the viewport. These control the snapping locations when moving an actor around. You can also change how large the increments of rotation and scaling are. The last icon opens a 4-window view to help position actors precisely. I will not be using this in this example. With the current level we put together, we can't do much other than watch some things fall and push them around a bit. To start, I don't want the objects to be white anymore. Let's change them to metal. Great, that works fine one at a time. But what if I had to change 10 or 100? What if I want the balls to do more than just roll around? Unfortunately, we can't do anything without creating some code of our own. Time to do some actual work. Unreal Engine uses a unique coding system called blueprints. Blueprints are intended to be faster and easier to code with compared to scripting, while being just as performant. Unreal Engine can also use C++ coding language to do the same thing, but that's for a later video. There is a lot of discussion about the performance of blueprints and how it is recommended that you should use C++ whenever possible. Personally, I haven't noticed a huge performance hit when using blueprints. Leave your thoughts in the comments. Let's start with creating a blueprint for our own ball. I created a folder called Blueprints, and in that folder, I right-click in the content browser and select Blueprint Class. You will see a list of common parent classes. We will talk more about these another time, but for this example, we will select Actor. This will create a new blueprint class in the content browser. So that I know by file name that this is a blueprint-based class, I will prefix my class with BP_. I will call this actor class MyBall. While this is a custom class, it is commonly just called a blueprint. I will call this just blueprint from this point forward and omit class from the end. We are looking at the viewport of the blueprint. The viewport is a way to see what your actor looks like and arrange the meshes if you have multiple in your class. I'm going to select Add in the Components panel and add a sphere. I will move this to the root. Not having the mesh as a root can result in odd behaviors and results, specifically when checking the actor's location. You will see that it stays the same even when you see that the actor has moved. That is because only the mesh component has moved. You can do this if desired, but setting the mesh as the root avoids this issue entirely. I set Simulate Physics to True and drag the actor into my level. We have recreated the balls already in the level. Let's change the material and see what happens. Ooh, gold. Nice. As you can see, all the instances of this blueprint change. This allows making changes to many objects quicker and easier in the level. The event graph is where we do our runtime coding. We see some default events already in the graph. We will start with the begin play event and remove the others for the time being. The begin play event runs as soon as an instance of this blueprint is loaded. Since we have some in the level, each will run the begin play event as soon as we hit play. If we were to spawn one at a later time, it would run as soon as it was spawned. To see the event run, I will use a print string node to display text in the editor viewport. The print string node is arguably the best debugging tool in Unreal Editor. You will see why shortly. The white pins are called execution pins. The red event node starts and the code flows through the execution line like water in a pipe, executing each node as it gets to it. When I hit play, each instance of my ball runs its begin play, and each one prints hello to the screen. You can see all 6 here. Let's remove all but one. Self, or a reference to self, is a way to get information from whatever instance is created. Once an instance is created, it becomes its own separate identity and will perform its code independently from the others. Getting a reference to self and then using the getDisplayName node and connecting that to your printString node will change the output to the display name of the instance object. You can see that the display names are the same as the blueprint name followed by a number. The tick event runs each and every frame while the program is running. Let's do something similar as we did in the begin play event, but print the object name to the screen. Let's have only one in the level for now. As you can see, there are many printing to the screen, and it is slightly different than before. This is the name that Unreal Engine uses to keep track of objects. Just know that the object name will be different than the display name. The name is being printed each frame of the game. So if the game is running at 30 frames per second, it will print 30 times each second. In the tick event, you will see a delta seconds out parameter. This is the amount of time between the last tick event and this one. It's green because it's a float type variable. Variable types must match to be connected. Thankfully, Unreal Engine can convert most on its own. That's what this node that just appeared does. Now the delta time is being printed each frame. The actor begin overlap node is a troublemaker for me and I don't use it. I'll talk about alternatives later. Oh no, I deleted the events. Whatever should I do? Over in the blueprint panel, you will find other functions that you can add code to, but not begin play or tick. Right-clicking in the event graph and searching the event you need is where to find it. There are also events that are component-based. Find these near the bottom of the details panel with the desired component selected. With the mesh component selected, let's try out the onComponentHit event. Let's just print hello when this event triggers. As the name implies, the event triggers when it hits something. By default, it really only triggers when it hits the player. These pins are the information about what hit the ball. Let's print the display name of what hit the ball. We can see that it was the player hitting the ball, clearly, since we controlled the player into the ball. Let's try to get different information. How about the class of the thing that touches the ball? We can change the getDisplayName node to a getClass node. From that, we can ask, is it the same or equal to the class of our choice? I know that the default player class in the third-person template is BP_third-person character. This equal node will return true or false. We use a branch node to control the code flow based on these results. If it's true, it will print that it hit the player. If it's false, we will do nothing. And we see it works. For fun, let's print that it hit something else. Nothing's happening. The first thing to check is that the hit events are being generated. In the collision heading of the mesh, we see that simulation generates hit events is disabled. Let's turn that on and test again. Okay, geez, that works. We can turn that back off again and set the false branch back to nothing by deleting the print screen. Let's make something happen when the ball touches the player. How about making it change color? First, we drag out a reference to the sphere mesh and use the set material node. Set nodes change the value, and get nodes tell you what the value is for all nodes. There is only one material for the sphere, so we leave the index at 0 and choose a material to change to. We see that each ball that we touch changes as we touch it, and not all of them. Let's do some more. How about we make a way to change it back to the original material? We will create a variable that will tell the code we are ready to change back. We will use a boolean
Boolean
to give us a true or false. True will mean change back, and false will mean stay changed. This little eye here exposes this variable. When the eye is closed, the variable can only be changed in the event graph. Toggle the eye open, and you can see the variable in the details panel. I will show when and why to do this soon. Let's bring back the tick event. We can branch based on our changeback variable. For now, let's just print this to the screen. While the game is running in the editor, press F8 to stop controlling the character and select the ball. The detail panel should now be populated, including the variable we created. Check that box to cause the code to run the true branch. We don't need the false side of the branch for now, so we can remove the print string node. Let's make the material change back after a set amount of time. We will need some way of keeping track of time. A float variable will handle this nicely. I don't need the change back variable to be exposed, so I will close the eye. We will need a way to remember what material we started with so we can change back. Let's bring back the begin play event and get the material of the mesh. Dragging off to nowhere will open a node menu, and near the top is a promote to variable option. This creates a variable of the correct type automatically. In this case, it's a material interface type variable that I named starting material. Keeping your blueprint code clean is important. It's easy to start crossing lines, and soon everything starts looking like spaghetti. Comments are a great way to keep sections separate and for others to read your code easier. Select a group of nodes and press C to create a comment. Let's start counting with our timer. Get the value in the timer variable and add the delta time. Remember to set that result back to the timer variable to save it. We will put it first in the tick event so that it updates the timer every frame, no matter what the other variables have to say about it. On the true side of the change back branch, when we are ready to go back to the original material, we will make sure that enough time has passed by comparing the value in the timer to a time length of our choice. I will choose 5 seconds. Even though the default value is 0, I will still make sure that the timer starts at 0 when begin play runs. After enough time has passed, we will reset the timer to 0. We need to tell the variable that we can change back. For now, we will just say that we are ready to change as soon as we change to the rust material, since we have a timer delaying the change back. And after the change back, we will clear the change back variable. Let's test this now with the print string. We can see the material change, and after a few seconds, the text appears. Time to make the material actually change back. We can copy the code that first changed the material and paste it in place of the print string node. Remember how we stored the starting material in begin play? We can get that here and plug it into the material to change back to. Now it changes back. I don't like that the time doesn't restart if we touch the ball again before it changes back. Let's improve things. First, we can set the timer to 0 when the ball is touched. We can improve performance by only running the timer if we're wanting to change back and the timer isn't above the time limit yet. No point of doing work if we don't need to. Everything seems to work as intended, but I want to do more. How about we make the ball move away like it was kicked? In Unreal Engine, we can use impulses. Impulses are short blasts of energy. These only work on meshes that are simulating physics. We can control the direction of the blast with a vector. I'm not going to go into too much detail about vectors in this video. There's way too much. But quickly, a vector 3, as used in Unreal Engine, can be both a single point in 3D space and a direction with magnitude. Or an amount of force. So the impulse in the add impulse node puts a force on the mesh in the direction, and the larger the number, the more force is applied in that direction. I'll just use positive X so the ball moves away from the player, right? Let's guess at some numbers until we get something that starts to work. After being woefully low on the guesses, the ball starts acting like I planned, but it's always moving the same direction no matter how I kick it. If you can't guess why, back up the video to the world and local space discussion. I'm going to switch the add impulse node with an add impulse at location node. In the on-component hit node, we see a hit pin. This is all the data about the moment of impact between the ball and the player. The hit pin can be broken, and we can see all the parts that are inside for us to use. The location parameter is the point of contact in world space, and we can connect that over to the add impulse at location node. I'll print that location to the screen just to make sure that things are working. We can get the direction of impulse by figuring out the location of the actor and the location of the ball and subtracting them. Then, multiply that direction by an amount called the scalar to increase the magnitude of the impulse. I think the vector is pointing from the ball to the player. We can just reverse the subtraction to invert the vector direction. Also, the direction is going from the center of the player to the ball. It should be coming from the player's foot. We could just move the point on the player down a bit to correct for this. Now the ball is kicked. I want to see a slight upwards kick. We could just take the resulting impulse calculation and add some power to the upward axis. In retrospect, since we are calculating to the ball's center, we should just add the impulse to the center. I'll change back to the add impulse node, but keep all the calculations. I see the ball jumped up ever so slightly. I need more up to it. There we go. The ball's flying like a real footballer or soccer player. What the hell do you call him? How about we learn to make a box move around like a moving platform? We will start with making it move in a straight line. First, we need to make a new actor blueprint and add a cube mesh. In this scenario, making the mesh the root of the actor isn't recommended, but I will because I want to show you a common issue that developers have when moving actors to a point. I will change the material so our platform stands out a bit and place it in the level. We will go to the event graph and work in the tick event. Let's try a set actor location node. This node does what is implied and instantly moves the actor to the location set in the node. Leaving it at all zeros, we see the cube in the ground at 0, 0, 0. Now, let's get the current actor location and add 10 to the x-axis. Since this happens every frame, we will repeatedly get the location, add 10 to the location in the x-axis, set the actor to the new location, and move on to the next frame. And the box is gone. 10 is too much, let's try 2. There is a huge problem when moving things each frame. Every computer is different and runs programs slightly differently than each other. Using the console commands, I will use a testing feature that artificially creates unsteady frames per second from 1 to 30 frames per second. I will also turn on the FPS counter. Now that the FPS is much lower than before, the box moves much slower since there aren't as many frames each second. Speed is distance over time. FPS is not a steady time, and results in the speed being inconsistent. We need to use a steady time, like seconds, or a portion of a second. We talked earlier about delta time. We can use this to calculate how far the platform should move each frame. We add a new variable named movement speed, and open the eye to expose it. Now we add that to our x-axis before setting the actor location. Change the movement speed to something like 200 for now. If we are running at 30 FPS, that means that each frame should take 0.03 seconds. That would be our delta time. 200 multiplied by 0.03 seconds is 6. That means this block would move 6 units in that frame. That's a little fast. Let's shoot for closer to 2 like we had and try 125 movement speed. 125 times 0.03 equals 3.75 units per frame. Now the platform movement will be steady. If a frame takes longer, the box will move further per frame. Now the box will move at the same speed on every computer or device regardless of its rendering power. Let's play with the fact that we expose the movement speed in the platform. Alt-drag to make some copies and change a couple speed variables. You can see that each one moves at a different rate. Now you can control the speed of each platform easily within the level, but the platform just goes off into the sunset forever. This isn't very useful. We should have it come back. Better yet, we should have it go to a point and then return. As of right now, we can only move it along the x-axis. In the blueprint, I'm going to add another mesh to act as a point to move to. I'll make it smaller and blue to stand out. When selecting the platform actor in the level, you can select the target mesh component and move that independently from the platform mesh. I'll put it out here somewhere. I will need to remember where the platform started at, so I will save that variable in the begin play event function. I really don't want a code in the tick event here, so I will make a custom event named move to target where I will do the work to move the platform. After the starting variable is set, I want to start moving to the target by right-clicking and searching for the name of the event we just created and selecting it under the call function heading. Let's do a quick test to make sure that the code is doing what is expected. Everything looks good. Let's use a timeline to move the platform. Right-click and add timeline to your graph, double-click to edit it. Click on the plus track and select Add Float Track. I will name my track Alpha. You will see a timeline graph. The length is the amount of time it will take to run the graph. I will leave this at 5 seconds. Right-click on the graph and add 2 keys. The first at 0 time and 0 value. The second key at 5 seconds and 1 value. These buttons resize the graph and fit it to the view. Back in the event graph, connect the Move to Target event to the Play from Start pin in the timeline. Update is the change each frame. Once it fully runs the timeline, in this case after 5 seconds, it will execute the Finished pin. We're going to let Unreal figure out where the actor should be between the start and target locations. Let's bring in the start variable and where the target was set to. We will use a lerp node. Lerp, or linear interpolation, is a way to get a value along a line based on a third value, alpha, set 0 to 1. In this example, 0 being at the start point and 1 being at the target point. An alpha of 0.5 would be exactly halfway. Off of the update pin, we will set the actor location based on the results of the linear interpolation calculation. Remember a bit ago when I talked about not setting the mesh to the actor root? We have arrived at why not. Since the target is parented to under the cube mesh, if you move the cube, the target will move also. It will always keep the same relative location from the root, which I set as the cube mesh. The result is that the target keeps moving away during the update phase of the timeline, and the calculations keep changing, and the cube flies off to infinity, trying to catch a carrot on a stick. To correct this, we need to have the calculated start and end points remain the same for the duration of the lerp calculations. We can do this by saving the target location, just like we did for the start location. Now the cube moves to where the target started and stops. I don't want the target mesh to show up when I'm playing the game, so I can enable the hidden in-game setting. Great. A nice smooth movement from start to finish. Let's make it move back. You could always reverse from the end to play the timeline backwards. This will work, but would require telling the code when to play forward and when to play backwards. I would rather create a new event function that handles moving the platform from the target back to the start location. On finished, we will call the move to start event function. Now we can just copy everything and switch around the target and start locations and run it from the start again. Seems to work great. What if you want to change the speed? In this case, we can do that by altering the play rate of the timeline. The great thing about a system like this is that I can pick anywhere to set the target. We'll move between the target and start locations, even if it's above it or diagonally. If you don't like the abrupt change of direction, you can alter the timelines to create smooth curves that will slowly ramp up and slow down the platform acceleration at the ends of the travel path. I think that's enough for this video. On the next video, I will dive into blueprinting even deeper and start to explain better ways to code, ways to make your code easier to change around, creating a controllable pawn, and possibly start on a full game that you can follow along and make your own. As always, if you liked what you saw or found it helpful, like and subscribe to know when the next part comes out. Thanks for watching.